Hello everyone. In the previous lecture, we discussed the serial in, serial out shift register, including the register basics. We talked about the serial in, serial out shift left operation, serial in, serial out shift right operation, and also the required configuration and the timing diagram. We also discussed about the serial in, parallel out shift register configuration, which was advantageous compared to, in terms of speed, compared to the serial in, serial out configuration. Now today's lecture is the continuation of the previous lecture. My name is Shiv Charan Puri, Assistant Professor, PC Department, Asansol College. Now let's start with the parallel in, parallel out shift register. That is a PIPO configuration. Parallel in, parallel out. You see here. Now you can see in this circuit diagram, you can see here in the block diagram, it is the same D flip-flop, okay, as discussed in the previous shift registers, driven by the same clock. Okay. Now you can see here data is entered not serially but rather parallelly to all the D flip-flops, and also it is taken out parallelly. Okay. You can see here data is entered here ABCD parallelly, and the data is corrected at the same time Q0, Q1, Q2, Q3 parallelly. It is definitely a 4-bit configuration, or rather a 4-bit register. The parallel input and parallel output. So this is 4-bit. The circuit shows a 4-bit PIPO shift register where the inputs A to D are connected parallel to all the 4 D flip-flops. After triggering the first pulse at the pulse end, we can get all the 4-bit simultaneously. That means when the first clock pulse is applied, okay, so with the first clock pulse, this all flip-flop will see inputs A, B, C, D, okay, and in the first clock pulse only, the whole output will be taken, Q0, Q1, Q2, Q3. So it requires only one clock pulse to take input and output simultaneously. The ABCD input data have to be held constant to get the same output by attaching switches. So that's the challenge, that this input ABCD should be constant while the input is fetched by with the clock. Now, definitely, as we require a single clock to fetch all the data, so this is the fastest data transmission technique. Okay. The time for parallel data transfer is independent of the number of bits transferred in parallel, as shown in the figure. For 4-bit PIPO operation to be completed, we require one clock pulse. For n-bit PIPO, we require the same clock. That's the most advantageous part. That even if you have n-bit register, you require that time also one clock to completely take the data. However, communication between two computers to transfer the data, 8 bits, we require 8 such wires, and for long distances between them, longer wires are required. So that is a challenge. So this scheme is not economical. Okay, all long distance data transfer is taking place through CISO, though it is time consuming. Okay, and hardware cost is less, because for n-bit data you require n-bit long wire to fit all the data. So it will be very complex and cumbersome at the same time. The PIPO operation is shown in the table below. You can see here. This is the PIPO operation. Okay. So when there was no clock, okay. So when there was no clock, so when there is a 0 clock, you can see here 1011 was data, but still you don't have anything because it was cleared initially. Okay, so it will remain like that. As soon as the first clock is triggered, you see, simultaneously you get 1011. Okay. Provided by this ABCD input. So there is a delay of t second of 1 clock pulse. Next is the PISO, that is a parallel in serial out shift register. So this is PISO configuration, parallel in serial out. Okay. This is a 4-bit parallel in serial out configuration. Okay. The whole operation of the circuit is controlled by the shift or load pin. As you can see here, this is the input actually. Okay. Or rather, input means what? Input doesn't mean data input. Data input are A, B, C, D. But this is actually the control input. Okay. Here you can fit either 0 or 1. And depending on your 0 or 1, your whole circuitry will behave either as a load or as a shift register. Okay. The shifting operation is done with the help of AND gate 1 to 3 and loading is through the AND gate 4 to 6. I will explain it. Suppose you put here 0 or rather ground it. Okay. What will happen? If you put here 0, load bar will be 1. Okay. Or rather you see here, if you put here 0, what will happen? Here will be 1 and here will be 0. What is connected from here? From here, this is connected. Okay. This is connected. Okay. So you see here, and from here, this is connected. So from here, if you put here 0 or you rather load it, okay, what will happen is basically your 1, 2, 5, 1, 2, 3 will be on. Okay. And if you put here shift, what will happen? Here will be 1, here will be 0. Okay. So if you put here 0, there will be load bar will be 1. That means it will be a loading operation. So this line has to be 0, this line has to be 1. Okay. So if you put here 0 in a AND gate, 1 input 0, output is 0. Okay. So this is actually a this connection will basically discontinue. Okay. Similar will happen for other AND gates also. That is AND gates 1, 2, 3. Okay. So but if it is 1, it will be shifting operation. Okay. It will be shifting operation. That means here will be 1. So this gate will basically be enabled because now you can get the access from here. Okay. You can get the access from here and you can get the access from here. So finally it is nothing but a shifting operation, isn't it? So if you put here 1, it will be shifting operation. If you put here 0, there will be 1. So this B, C, D and obviously here the A. So that is A, B, C, D will be fed directly to the inputs. Okay. So this is how it behaves. This whole circuit will behave. That means parallel we are feeding the input. Okay. But serially we are taking the output. Okay. So in this circuit, the input bit A to D appears at output after 1 clock pulse. So we are having two mode as I told you. 0 parallel data into parallel data out operator. 1 giving serial shifting of 4-bit parallel data to the right to the successive flip-flop. When clocks are applied, the data are successfully shifted from the output of one flip-flop to the output of the next flip-flop. The operation is described below in the table. As you can see here, the whole, you see, if you are putting here 0, okay, then it will be, you see, 1011, everything is clear, okay. If it is 1, as you can see here, the whole operation is explained here, okay. So in this way, for 4-bit piezo to compute a requirement plus 4 is equal to 1 plus 4 is equal to 5 clock pulse. For an n-bit piezo, we require n plus 1 clock pulse. This is the right shift operation. To convert it to left shift, we have to reverse the connection towards left hand serial output data is something from Q0. So just you have to reverse the terminal, and you can also control the shifting. Okay, either you want to shift left or shift right. Okay, the mode will remain same. Just you have to change the orientation of the input and output. Thank you.